Hi, I'm Tim, and I'm presenting with Zhuozhao Li. We're talking about the different uses that the WorkQueue executor can bring to parcel applications. So just a bit of background. WorkQueue is a manager worker framework that dispatches tasks to workers and then brings them back to the manager node, and it can fulfill a lot of the same basic roles as the high throughput executor. It uses a pilot job system so that you don't have to wait in the batch queue, and you can send many small tasks and get them quickly placed. And it can pack multiple tasks on a node, so it's aware of resource requirements and it can try to pack those well. It also has some interesting extra features. So it doesn't assume that a shared file system is present. So it'll do transfers of data and other dependencies on its own. So that might be useful in certain situations, and we'll talk about that later. And it does its own caching of common input files, and that's useful for reducing the amount of time spent transferring these big files. And the exciting things we're talking about in this presentation are fine-grained resource management and automatic dependency management. So to get everything, the easiest way is to just use Conda. You can install CC tools, Parcel, Python, everything you need through there. And Parcel also supports pip. And once you've installed CC tools, you'll need to get some workers to connect to your Parcel application. So the recommended way to do that is with WorkQueue Factory. And that's a program that maintains a pool of workers, and it'll do batch submissions for you. In this example, through Condor, or we support SGE, Slurm, a whole bunch of other ones. And it'll automatically maintain a pool of workers in some size range, and then as workers die, resubmit and maintain that pool to keep your workload running. So how this fits together is Parcel sits on top of the WorkQueue executor, which sends these function calls out to worker nodes and brings back the results for you. So fine-grained resource management is something that Doug was talking about a bit in the presentation earlier today. So WorkQueue has a notion of resource requirements on tasks. So a task can specify the cores, memory, and disk that it requires, and workers also measure that on the node when they start up. So WorkQueue will send tasks out to worker nodes that are large enough to fit their needs. And if a task is small, then you might be able to pack several of those tasks onto a single worker. So in this example, we have a 4-core task and a 3-core task, and those can both fit on an 8-core worker. And there's even an extra core left over. So if you're careful about those resource annotations, you can pack your tasks much more efficiently, or WorkQueue can pack them for you. So WorkQueue has a couple of different modes that you can use. If you don't specify anything at all, it'll be conservative and assume that each task consumes an entire worker. If you do write out specific resource specifications, WorkQueue will take your word for it and pack tasks onto nodes following those specifications, but tasks may use more resources than they said they would. And WorkQueue also supports automatic resource labeling, which means that it will measure the actual resources used by your tasks and then infer efficient labels for those allocations as you go without input from you. So the situations when that would be useful is if your tasks vary in size and you might not even know in advance what the size is. And also if your workers are heterogeneous or vary in size. So we don't want to just do the one task per worker mode because there's all that extra space on the workers that's not being used. So that's wasted throughput. And if we aren't careful and we pack too many tasks on a worker, we'll run into resource contention, exhaustion of resources, thrashing, all sorts of nasty behavior, and start having jobs failing and needing to be retried. So the basic idea of what happens in WorkQueue's automatic labeling is that we have a set of workers. Here we just have 2. So WorkQueue will choose some initial allocations inside those workers and then start sending some tasks to those allocations and watch what they do. And if a task exceeds its allocation, say it uses too much memory or tries to use all the cores on the machine, WorkQueue will come by and whack that task on the head, kill it, and start it again in a larger allocation. And in this case, on a separate worker. So the idea is that WorkQueue can keep doing that and measuring stats about the actual usage from your tasks or your parcel function invocations. And then it'll figure out appropriate resource labels so it can pack them more efficiently based on their actual behavior. So as an example, we applied this feature to a high energy physics application. This isn't parcel specific. This is just a basic WorkQueue application, but the system can measure the resource usage and the memory usage for these different tasks, and you can sort of get a histogram of the requirements, and you can see there's some variability there. So WorkQueue has a whole algorithm for choosing what the initial allocation should be, how it needs to scale up the allocations when things run over. And if you want to read more about that, there's a paper I can point you to. But the idea is that this WorkQueue algorithm gives you pretty good performance from the initial pick, and it doesn't require a lot of interaction or explicit labeling. So here's some results from a paper that we're working on now using a drug discovery pipeline with COVID-19 research. So here, Oracle is the explicitly labeled requirements, the correct numbers for each and every function. Auto is letting WorkQueue figure it out on its own. Guess is if you just make a static guess, like, I don't know, each parcel function probably takes 4 cores. And unmanaged is assuming that each function needs the entire node to run. So we have strong scaling on the left and weak scaling on the right. And you can see that WorkQueue can automatically get pretty close to optimal packing of these tasks and reduce the amount of time that your applications take to run. So that's great for increasing throughput. So the other big feature that we're talking about here is automatic dependency management. And I know this has been mentioned a few times in some of the user stories. So if you have your apps that need to import libraries, I just have a simple little app that imports NumPy here and doesn't do a lot of useful work. But if your worker nodes don't have the same Python environment, say they are missing the library that you need, or they might not even have the correct Python version or Python installed at all, then your parcel functions are going to come back with some nasty exceptions because they can't import what they need. So the reason for this is that the dependencies are sort of a hidden dependency in the parcel apps. If you have a shared file system, they can be transferred in the background behind parcel's back, but we don't have a lot of management set up to deal with that. So using the WorkQueue executor, we can handle that better. So this might happen in some batch systems, like Condor often doesn't have shared file system support. Some sites might not have shared file systems, or you might be trying to run an application across multiple sites. So you wouldn't be able to rely on a shared file system to set up your Python environments for you. And if you're running things at large scale, again, as Doug mentioned this morning, if you're running things at large scale, those imports themselves can be pretty expensive. So it's possible that all these small functions starting up really hammer the shared file system and cause performance issues. And there's some research we've done that shows that if you're interested. So CC Tools includes some tools to help deal with this by automatically preparing packages and running the functions inside those. So the idea is you have your Python app that has its imports. We have a tool to analyze that and generate a specification saying what imports this piece of Python code actually needs to run. And then using that specification, we can generate a packaged environment. So it's just a tarball. It's easy to ship around, but it includes all the Python code that you're going to need to run this application. And then when we actually run on worker nodes, we ship that tarball across to them and then run the code inside that environment. So then we no longer have to worry about whether the worker has NumPy or whether Python is installed or there's a version mismatch or anything like that. So the WorkQueue executor is set up to handle these analysis and packaging steps automatically in the background for you. It's sort of a beta feature, so there's some rough edges. It'd be good if you get in touch with us so we can sort of figure out how to get things going. And it's still under development. But we would love to get people trying some of these WorkQueue features out. And then again, I would like to stress that Python itself can be shipped. So if you have a situation where your worker nodes have version mismatch or don't have Python, this is a great solution. And WorkQueue's built-in, covering that up, WorkQueue's built-in caching means that you don't have to spend a lot of time retransferring these environments. WorkQueue will try to send tasks to workers that already have the environment set up. So you can minimize the overhead that way. So to turn on these features, there are a few options in the WorkQueue executor. Auto label equals true turns on the measurement and allocation labels. Auto category equals true is a good idea to turn on to measure each parcel app separately. And pack equals true turns on the packaging of environments. Are there any quick questions before we move on to the demo? Okay. So I'm going to cover the dependency management first. This notebook is set up to run in a Conda environment that has Parcel, CC tools, NumPy, like in my example, all set up in advance. So I'm mentioning that at the beginning of the notebook here. So let's say we have a little application that we want to run. Again, doesn't do something particularly useful, but a little application that will invoke NumPy. So we can run it locally, that's fine. So far, so good. So now let's say we want to scale up and use Parcel. So we get all our imports. We configure Parcel to use the WorkQueue executor. I have it set up not to set up any workers because I'm going to do those manually. Normally you would set it up to submit your batch system or run locally or something. But let's configure Parcel. And now we'll define our Python app that's able to run through Parcel. And note that Parcel apps need to specify their imports within the app. And then we use that to automatically figure out the software dependencies.
Not to derail you, Tim, just a quick question. Why did you need to manually start the worker? Or what, is there, maybe that's not important, but I'm just curious.
Oh, yeah. So if you were doing this for real, you would set up the provider and either run them locally or, submit jobs through your batch scheduler or something. But for this notebook, I'm running a worker manually in a different environment than the notebook. So it's easier to just sort of show that by hand here.
Gotcha, thanks.
Yeah. So once we define the little Python app, then we try to run it, get the result. But as you can see, the notebook is hanging because there's no workers yet. So let's hop over and run WorkQueue worker. So now the worker connects and we get a module not found error because this worker was running in a bare bones environment that didn't include NumPy. So you could imagine this is on a different site or shared file system isn't available, whatever your situation happens to be, just the worker Python environment doesn't match the where the notebook is running. So now let's tear down that DFK and let's do another config. It's pretty much the same, except now we turn on pack equals true. So that's going to turn on the automatic analysis and packaging features. So we run that config and let's try running our function again. And we'll go over to our stripped down environment and run WorkQueue again. Send it a worker. And now the worker is connected. It's going to take a couple of seconds. There's a bit of an overhead because we have to ship the environment over to this brand new worker. But success. Even though the worker doesn't have NumPy available, we shipped it over, unpacked it automatically. The Parcel code doesn't really have to be aware of it. It just happens in the background. So are there any questions about this feature before I hand it off to Zhuozhao?
I don't have a question, just a comment. This is so awesome. This would we can just point everybody to WorkQueue now whenever we get the the very common question in the help channel about why the workers aren't connecting, which is usually because it's a different.
Yeah, yeah. I guess in the lead up to the workshop, we've been digging up some of those rough edges and stuff that needs to be fixed. So I'm going to be putting in some issues and pull requests to get this more out of the beta state. But yeah, it would be great to get users using this stuff. It simplifies a lot of the things you have to deal with in some of these more heterogeneous configurations.
So I have.
Oh, go ahead.
So yeah, this looks very interesting. So I have a couple of questions. One of them is that you already do some resource monitoring for your analysis. How does that map onto the concept of the parcel monitoring? And is there any plan to actually add the parcel style monitoring into the WorkQueue executor?
So I'm not aware of any plans to add the parcel monitoring to WorkQueue. Zhuozhao or some of the other people on the team might have some thoughts about that. But I would say that the WorkQueue monitoring is sort of maybe a lower level fine-grained type monitoring, in that we're using, as Doug mentioned this morning, we're using some of these Unix resource monitoring things and so that we can catch stuff that might go sort of outside the Python function. If it calls other tools or starts doing weird things, we can track that and pass that back up. It probably would be useful if we would integrate that more with parcels resource monitoring. So that might be a good direction to look at, but I'm not aware of anything on that right now.
Okay, and one last question. So you monitor, you allow, the WorkQueue can handle things like a number of cores, the memory footprint, that kind of thing. How about execution time? So if you have a series of tasks that with varying input will take varying amounts of time, and you think that you have a fairly good ceiling on that time, can you make use of that information to prevent tasks from attempting to be executed on a batch machine that is not going to necessarily have enough time to complete the execution?
Yeah, so at the moment, WorkQueue doesn't really treat time as a first class resource, but I was hearing the same example in the talk earlier, and that is something that comes up quite a lot, because a lot of these sites have the hard limits that you have to specify. So either with WorkQueue, or we're working on sort of the next generation WorkQueue replacement that'll be integrated into Parcel as soon as we have it ready. That's definitely stuff that we would be looking at in the future for resource management, but unfortunately we don't have that as one of the first class resources right now.
Actually, Ben, can you jump in on that? Because I know that you've done some work on execution time.
Yes, so WorkQueue is able to stop the task if it goes above the time that you specified. What we cannot do right now is to stop the task for being submitted if the batch job is going to finish soon. So if the worker is on a batch job and that job is going to be killed soon, we are going to still schedule the task. Like, I think that's what Tim is talking about, not being first-class citizen.
So I think, in the bigger picture, I think the plumbing for all that stuff is very close to the surface. So we'd be happy to talk to you and understand your use case and bring those features to the surface. But I don't think that they're far away.
Yeah. Okay, thank you.
I have one more follow-up question. So, I mean, I know in previous projects I've worked on with WorkQueue, we've kind of done our own homegrown monitoring, but kind of following up on Tom's question about monitoring, is there anything new, like just WorkQueue specific, like do all of your users that are just using WorkQueue kind of do their own monitoring by parsing the logs and things like that? Or is there any plans to do kind of a more, I mean, I would imagine you could build some kind of tool that would be kind of a standalone log analyzer for, that knows how to understand WorkQueue logs.
Yeah. So there's another guy in our lab who's working on his PhD thesis of examining logs and debugging and pulling out stuff like that. So I can point you to him, but we have some tools for querying our catalog server that records the tasks that are running and the utilization and all that. And we have tools for processing our logs to come up with, plots or do an online visualization and some different things like that. So if you're interested in some of those, I'd be happy to talk afterwards.
So, and if I can elaborate on that, I think we have quite a number of tools for digging stuff out of the logs and visualizing it. I think our experience has been that everybody's interested in sort of a different slice of analysis.
Mm-hmm.
So I think there's always some amount of specialization to get what you want. But I think the architecture makes that easy in the sense that the system generates logs. We have tools that parse the logs, and if you need something different out of them, the tools are an easy thing to modify on the side.
Thanks, Doug. Good to know.
Yep. So if there are no other questions, I'll hand it over to Zhuozhao to talk about the automatic resource labeling.
Can you see my screen now?
Yeah, it was up a second ago.
Oh. Okay.
There it is.
Okay, good. So, hello everyone. I'm Zhuozhao. I'm currently a postdoc at the University of Chicago. So I will continue some tutorial to the WorkQueue executor in Parcel. So this one is mainly to cover the fine-grained resource management using the WorkQueue executor in Parcel. So first of all, that's how we install and WorkQueue executor and Parcel. So I will just skip here because Tim already mentioned that. So I will basically walk through three typical use of WorkQueue executor in Parcel, which are the default auto label and per task resource specification right here. So just a recap from Tim's talk. So the default one is to just launch one worker on every compute node, and there's no resource aware task packing or something like that. So default is actually suitable for apps that need to utilize the resource of the entire node. For example, like an app itself already does some parallelism internally to use all the nodes, to use all the resource on the node. And auto label is to enable WorkQueue to automatically figure out the resource needed for every category of tasks, and then automatically locate the task to use the computing resource efficiently. And the per task resource specification allows a user to specify the exact resource needed for an app. So I will go through all of these three default auto label and per task resource specification in this demo. So if we look at this cell, so this cell is just some basic import for this demo. So let's go to the second cell, which is the default config of the WorkQueue executor. So as you can see right here, the WorkQueue executor interface is quite similar to other executor interface, like the high throughput executor interface. So we already integrate the WorkQueue executor with the Parcel's provider interface. So anyone can deploy, the WorkQueue executor on many sites easily. So if we just load this default config right here, and then so for simplicity, I would just use the local provider here for the demo purpose. So this will just basically launch one WorkQueue worker on the local node. And so if we define a sleeper app right here, and the sleeper app basically just sleep for a short duration of time, and we know this app use minimal resource, right? So, and then we invoke this app. Let's define this app. And if we invoke this sleeper app for multiple times, and then within this default configuration, since each worker can only run one task at a time, so the following, so these sleeper tasks are essentially run in serial. So this can basically tell from the completion times. As you can see here, I already started this cell for a long time, but it's still hanging. So this basically means that the tasks are running for a long time. So, but this is essential. Yeah, okay. So I don't know why this one is super long right here, but it might be some file system issue because I run this notebook on a head node of a cluster of a machine. So this, but basically you can see that these sleeper tasks are essentially run in serial with this default configuration. So, but there are, if we use the multiprocessing CPU count utils here, you can see that there are actually many cores on the head on this local node. So there are 56 cores, but you know the sleeper tasks just use minimal resource, and this is not good to, I mean, this is default config is not ideal to run in tasks like this sleeper task that use only minimal resource. So, and this default config is more suitable for apps that need to use the entire computing node. So how can we use the WorkQueue executor for apps that do not need the entire node? So there are actually two ways to do that. So let me first just clean up the previous config and turn to the next two modes in WorkQueue executor, which are the auto label and per task resource specification. And this is useful for apps that do not need the entire node. And by using these two modes, you can, the WorkQueue executor will automatically pack the task on the node that has the available resource. So let's first see the auto label mode right here. So to enable the auto labeling, what we need to do is just set the auto label equal to true. And note that here we also set the auto category equal to true here. That's because, just like Tim already mentioned, the auto label in WorkQueue executor automatically monitor the resource patterns of apps by category. And by default, if the auto category, by default, the auto category is set to false. So this means that the WorkQueue executor categorizes all the parcel apps into one category, which is the parcel default. But however, different apps may present various resource patterns. So it's kind of better to categorize apps in a much finer grain pattern manner. So that's why we need to set the auto category equal to true here.
Sorry to interrupt.
Yeah, go ahead.
Oh, sorry. I can just put it in the chat. Can you clarify here, like what's a situation where you would want auto label equals true and auto category equals false? Like,
I think setting auto, so in that situation, that means basically all your parcel apps are like have quite uniform resource consumption. In that case, you will only use that set the auto category into equal to false. Then the WorkQueue executor will just categorize all the parcel apps into one category.
okay, but it's not like there's a
Yeah, definitely in the best practice, setting the auto category equal to true will enable, WorkQueue to automatically categorize different parcel apps based on their function name.
We might want to emit a warning or something if we find that configuration, because I think typically people want that. Okay.
Typically, yeah, that's true. So maybe we should just set the default to true even. Right. So yeah, that's the the config for the auto labeling. So if we load this config, and then I will try to show how this auto label works with some multi-core task. So here I define a task called MP task, which just simply use the multiprocessing module to mimic an app that use multiple cores. So so here I just use this define a stretch function that just lasts for a few seconds right here. So basically this MP task is to mimic a task that use multiple cores. And by default, it should use 2 cores and last for 2 seconds. So if we invoke this app, so that's how we invoke that. If invoke this app for 5 times, and actually you won't see much difference like the normal ones, like using the WorkQueue executor, or like the like disabling the auto labeling. So this is because the auto labeling so all the things in auto label, like the resource monitoring, profiling, and also allocation, are transparent to the users. But behind, so that's how the auto label works. So all of them are kind of transparent to the users. But behind the scene, let's take a deeper look behind the scene and see how the auto label works here. So here I define a pass log function, which basically just pass the debug logs of the parcel logs in the run info directory. So this basically just filter out the resource allocated to specific tasks. So if we define this pass log function right here, and then we use this pass log function, and then filter out what is the resource allocated to specific tasks. For example, this MP task right here. So we can see here the first MP task was allocated like 56 cores and this amount of memory. And this is basically all the resource on the local node. And this is because WorkQueue auto label try to assign all the resource on the local node to the first few tasks in order to profile the resource utilization of the tasks in this category. And after that, after the profiling, WorkQueue updates the resource for this category accordingly. And this, so you can see here, the later tasks of this MP task were allocated the correct amount of resources, which are around the 2 cores, certain amount of this amount of memory and this. And as you can see here, that's how we invoke, that's how the MP task should consume. It consumes 2 cores, right? So we can see the auto label just try to, so basically just the WorkQueue auto label monitor the resource of some tasks in this category first. And of course, this number, so you can see in this example here, we only profile 1 task, but this number can actually be tuned by another parameter in the config, which is the auto label window. So you can, by default, it's set to 1. So this means that WorkQueue auto label only profile 1 task to get the kind of like inference on the resource consumption. But definitely you can set it to any value you are comfortable with. And then WorkQueue will allocate the resource to the later task based on the monitoring for high throughput. And if a task fails because of lack of resource, WorkQueue will automatically retries the task with more resource. And this is all transparent to the user. So the above basically show how auto label works, and this is good for use case where one is not quite clear about the resource requirements of their apps. And actually, in addition to auto label, if you are quite clear about the resource consumption of your app, WorkQueue Executor also supports you to specify the resource requirement of a parcel app by using a specific keyword argument, the parcel resource specification. And there are actually 2 ways you can make use of this special keyword arguments to specify the resource requirements for each app. So the first one is just that you declare the default resource requirement when you define an app. For example, here, when you define an app, the MP task spec, you just declare the default resource requirements for this app. So using this keyword arg. And currently in WorkQueue Executor, only 3 resource types are supported, which are the cores, memory, and disk. So that's how, so if you invoke this app, like using this directory, and you can see, so let me first run this cell, so which is to define the app. So if you invoke this app without further specifying the resource requirements, so you can see we don't specify the keyword arguments in this invocation. So let's run that. We don't specify that, and then, so in this case, WorkQueue executor will allocate each invocation the default resource when we define the app, so which is this value right here. So it takes a couple seconds to run this task. So okay, so it's done. So if we pass the logs again and see that filter out what's the resource allocated to this task, you can see that these tasks are allocated the default amount of resource, which exactly match the definition right here. So that's one way to specify the resource requirements of this app. And the other way is that you can, when you invoke the app, you can dynamically change the resource specification for this app. For example, when you invoke the app for 3 times, you can specify the resource requirement for these 3 apps for 3 times, which are the 3 corresponding to 1 cause, 2 cause, and 3 cause. So if we run this one, then let's wait a couple seconds right here. And if we run this one and then pass the logs again, and you will see that these 3 tasks were allocated the exact amount of resource, which are 1 cause, 2 cause, and 3 cause. So that's how the resource specification with the WorkQueue executor in Parcel. And I think many people today mentioned that they expect Parcel to place the task in a resource-aware manner. So like Tom already mentioned that they all have different executor to run for different tasks, right? Just different type of tasks. So I think that's maybe the WorkQueue executor is probably a good one to try here. So that's the resource specification here. And it's also worth mentioning that any resource specification will override what the WorkQueue auto label in first. For example, so previously we specify all 3 types of resource. But what happens if we only specify 2 types of resource? So if this one is with auto labeling enabled, we do not have to specify all the 3 types of resource. And we can choose to specify 2 of them, for example, like cause and disk. And when you run them, the WorkQueue executor auto label will automatically figure out the gap, what is the resource needed for the memory here, because you see we don't specify memory here, but it's allocated the correct amount resource of memory. So with auto label enable, we do not need to specify all 3 types of resource, and the auto label will automatically fill in the gap. But with auto label disable, if we do not specify all 3 types of resource, the WorkQueue will allocate all the resource of the worker, which is exactly the entire node to run the app. And this is probably not a configuration, not the right configuration we should use. So this use case is totally abandoned, totally blocked in Parcel WorkQueue executor. So I think that's all I have just for a quick demo to find the resource management with WorkQueue executor in Parcel. So any questions for this one? Seems no. Maybe leave to Kyle.
Sorry, I was speaking to myself again on mute. Yeah, I think we're probably at the end of the day. We're a few minutes over now, so I think we'll say thank you, Zhuozhao, Tim, and Ben for those tutorials. They were all excellent. We will get them up online and share the notebooks so that others can go through them at home. So that's the end of our sort of scheduled programming for the day. If you want to stick around and you have any questions or anything you want to chat about, feel free to stick around. We'll be here for the next 20, 30 minutes. We can use breakout rooms, etc. Thanks a lot, everyone, for coming along today. We appreciate it.